Aboard an orbiting laboratory, a small object can remain beside you without choosing a floor. A pen released from the hand does not drop to the deck. It stays nearby, turning slightly as air currents move through the cabin. An astronaut can pass through a hatch face first, feet first, or sideways, and each approach works equally well. The walls may carry labels and handrails that suggest an intended orientation, but the room itself does not insist upon one. This is not because Earth has stopped pulling. At the height of the International Space Station, Earth's gravity is still strong. The station, the people inside it, and every loose object in the cabin are falling together. Their sideways motion carries them around the curve of the planet, so the surface keeps dropping away beneath them. Nothing inside presses steadily against the floor, and the familiar sensation of weight disappears. Without that pressure, the body loses one of its oldest reference points. On Earth, vertical direction seems built into reality. Rain moves toward the ground. Smoke rises through the air. A glass placed on a table remains where it is. Trees grow away from the center of the planet while their roots extend toward it. Nearly every room, road, tool, and gesture has been shaped by the same dependable pull. Yet this arrangement belongs to Earth. It is not a rule that fills the universe. Near the moon, down would lead toward the moon's center. Near an asteroid, the same word would point toward a much smaller body, and the pull might be so weak that a careless step could become a long arc above the surface. Inside a rotating habitat, down could point outward toward the spinning rim. In a spacecraft coasting between worlds, there may be no natural down at all. Space offers positions and motions, but it does not provide a universal ceiling. That simple absence changes the meaning of a question that sounds almost childish at first. If there is no permanent up, what would it mean to travel upward through the solar system? Astronomers can choose a useful answer. The planets do not surround the sun in a random swarm. Their paths gather around a broad shared plane, like many tracks laid across one thin region of space. Earth's orbit helps define the reference surface called the ecliptic. To move up through the solar system can therefore mean traveling away from that surface, toward the directions above or below the planetary orbits. Nothing blocks those directions. There is no boundary overhead, no hidden shell, and no region where motion becomes forbidden. The difficulty comes from the motion already carried by every spacecraft launched from Earth. Before a rocket leaves its launch pad, it is already moving with the turning Earth. More importantly, it is traveling with Earth around the sun. That solar motion does not vanish when the engines ignite. It becomes part of the spacecraft's path, an inheritance from a planet that has been circling the sun for billions of years. Most missions make use of that inheritance. They travel through the same broad plane as the planets, adjusting speed and borrowing gravity from worlds encountered along the way. A mission that climbs steeply away from the plane must reshape that inherited motion instead of simply building upon it. So the missing direction is not missing at all. It is present above the planetary paths, and below them, open and nearly empty. But reaching it asks a spacecraft to turn away from the oldest motion it possesses. To understand why that turn is so costly, we first have to see how the solar system became a plane. Long before there were planets, there was no solar system plane to climb above. There was only a region of cold gas and dust spread through part of the Milky Way. It was not shaped like a finished disk. It had no clean edge, no central star, and no orderly set of paths. Its material moved in many directions at once, disturbed by turbulence, nearby stars, and the gravity of the cloud itself. Then part of that cloud began to collapse. Gravity drew matter inward, gathering scattered particles into a smaller and denser volume. As the cloud contracted, one faint feature became increasingly important. The original material had not been perfectly still. It carried a slight overall rotation, That rotation may once have been almost too small to notice, but shrinking changed its effect. A skater turning with arms extended rotates more quickly after drawing those arms closer. The motion does not appear from nowhere. The same rotational momentum is being carried within a smaller space. A collapsing cloud follows the same broad principle. As its material falls inward, its shared rotation becomes faster. The cloud did not become a simple spinning sphere. Gas and dust were still crossing through it on many different paths. Some particles moved with the general rotation. Others rose above it, fell below it, or traveled against the local flow. In a thin and nearly empty modern solar system, such paths might continue for a very long time. Inside a collapsing cloud, collisions were common. Each collision changed the motion of the material involved. Movements that opposed one another tended to cancel. A particle passing upward could strike material moving downward. Their vertical motions were reduced, and some of that ordered movement became heat. That heat could then escape as radiation. The motion around the common center behaved differently. Most of the cloud shared some part of the same rotational direction. Collisions could rearrange that motion, but they could not erase the cloud's total angular momentum. Little by little, movement above and below the emerging plane was damped, while circulation around the center remained. The cloud flattened. This did not happen in a single smooth moment. It was an extended settling, shaped by gravity, collisions, pressure, magnetic fields, and the movement of material through a changing environment. Near the center, matter became increasingly dense. Farther out, a broad rotating disk took form. The young sun grew within the middle of that disk. Before it began stable hydrogen fusion, it was a protostar, gaining mass as material continued to fall inward. The surrounding disk contained gas, ice, mineral grains, and countless small fragments. These particles met, stuck together, broke apart, and met again. The first solid structures were tiny. Dust grains became larger aggregates. Some survived enough collisions to grow into bodies measured in centimeters, meters, and eventually kilometers. Gravity then became more effective. Larger objects pulled in smaller ones, and regions of the disk developed into planetesimals and planetary embryos. The planets would inherit the disk's motion because the disk was the place from which they formed. They did not begin as finished worlds and later agree to circle in one shared direction. Their common orientation came first. The bodies themselves emerged within material that was already moving around the young sun in a flattened flow. This is why the major planets travel the way they do today. Their orbits are not perfectly identical. Each has its own inclination, eccentricity, speed, and long history of gravitation encounters. Yet most remain close to the same broad plane because all of them carry the memory of the protoplanetary disk. Even after more than 4 billion years, the original structure has not been fully erased. Earth remains close to that inherited plane. Venus and Mars move near it. The giant planets follow it with only modest departures. Many asteroids occupy a thickened band around it, and much of the Kuiper belt still preserves the same general orientation far beyond Neptune. The flatness is not absolute. Mercury's orbit is tilted more than those of the other major planets. Pluto follows a steeper path, while some distant objects move at far greater inclinations. Comets arriving from the outermost reaches can approach from almost any direction. These exceptions do not undo the pattern. They reveal what happened after the disk formed. The early solar system was crowded and unstable. Growing worlds disturbed one another. Large bodies scattered smaller ones. Some objects collided, others were thrown inward, outward, or onto tilted paths. The giant planets may themselves have shifted position, while the solar system was young, reshaping populations of asteroids and icy bodies as they moved. Close to the sun, the old disk remains easy to recognize. Farther away, the pattern becomes less strict. In the distant Oort cloud, the solar system may no longer resemble a disk at all. Long-period comets suggest a nearly spherical reservoir of icy objects, scattered into a wide range of orbits by the giant planets, and later influenced by passing stars and the gravitational field of the galaxy. There, above and below lose much of their special meaning, but the planetary region remains unmistakably flattened. The worlds, moons, asteroids, and most spacecraft occupy a relatively narrow volume compared with the immense distances separating them from the Sun. The plane is not a physical surface. Nothing touches it. It is a geometric reference created by shared motion. You could pass through it without noticing. No instrument would record a boundary crossing unless it compared your position with the orbits around you. And yet, this invisible plane shapes almost every journey humans have sent beyond Earth. A spacecraft headed toward Mars, Jupiter, Saturn, or the outer planets is already moving through the region where useful destinations can be found. The planets lie near the same inherited sheet because they were assembled from it. Their gravity can be used along the way because they remain within reach of one another's orbital neighborhood. The solar system's flatness is therefore more than an image in a textbook. It is a record of formation preserved in motion. Every year, Earth completes another path around the Sun. Every year, it retraces the circulation once carried by gas and dust before Earth existed. The ground beneath you is part of a planet still following the direction established in that early disk. A spacecraft leaving Earth receives the same inheritance. It begins not from rest, but already moving with the planet through the old plane. To travel among the worlds, this is an advantage. To turn away from them, it becomes the central problem. The direction above the disk is open. The motion along the disk is already there. A spacecraft leaving Earth does not begin its journey from stillness. Even before the launch vehicle rises from the ground, the entire launch site is moving. Earth turns beneath it. Earth also travels around the Sun at nearly 30 kilometers per second. The Sun, carrying Earth and every other planet, moves through the Milky Way. Motion is already present at every scale. For a mission within the solar system, the most important inherited motion is Earth's orbit around the Sun. The spacecraft receives that velocity automatically. Its engines do not have to create it. The rocket may change the spacecraft's path relative to Earth, but once the vehicle escapes Earth's immediate gravitational control, it is still circling the Sun with much of the motion the planet gave it. This inheritance is one of the great advantages of launching from a moving world. A mission sent outward can add speed in the direction Earth is already traveling. A mission headed inward can reduce that speed, allowing the Sun's gravity to draw the spacecraft toward a smaller orbit. A mission traveling to another planet can enter a carefully shaped path that meets the destination months or years later. Most interplanetary travel is not a matter of pointing directly at a planet. The spacecraft and the planet are both moving. Engineers choose an orbit around the Sun that intersects the planet's future position. The spacecraft follows a long curve, arriving where the world will be rather than where it was at launch. These paths work well because the planets occupy roughly the same broad plane. A spacecraft traveling from Earth to Mars does not need to turn sharply above or below the solar system. It adjusts the size and shape of its solar orbit while remaining close to the region both planets share. The same is true for most missions toward Venus, Jupiter, Saturn, and the smaller bodies between them. Climbing steeply away from the ecliptic asks for a different kind of change. Velocity is not merely speed, it also includes direction. Two spacecraft can be moving at the same speed while traveling on completely different paths. Turning one velocity into another requires changing the direction of motion even when the number shown on a speed indicator remains the same. This is easy to overlook in daily life. A car can turn a corner because friction between its tires and the road provides a sideways force. An airplane changes direction by using its wings to redirect the air flowing around them. A boat pushes against water. Each vehicle is surrounded by something that can help bend its path. A spacecraft between planets has no road, atmosphere, or ocean. To turn, it must fire an engine, release propellant, or pass through the gravitational influence of another body. A change in direction must be paid for just as surely as an increase in speed. Consider a spacecraft moving around the Sun beside Earth. Its motion lies almost entirely along the ecliptic. To send it toward the north ecliptic pole, the direction perpendicular to that plane, the spacecraft cannot simply add a small upward component and expect the old motion to disappear. The original sideways velocity remains. A brief push above the plane creates a tilted orbit. The spacecraft begins moving upward, but it also continues racing around the Sun. Its new path becomes a sloping curve, crossing the ecliptic again elsewhere, rather than rising vertically and leaving the plane behind. This is how most inclined orbits behave. They pass above the reference plane for part of each revolution, cross through it, move below it, and return again. The orbit is tilted, but the spacecraft remains bound to a path around the same central body. A small tilt requires a manageable adjustment. A large tilt requires much more. The relationship can be described through a plane change maneuver. The cost rises with the angle of the turn, but it also depends on how quickly the spacecraft is moving when the turn occurs. At high speed, even a modest redirection can demand a large change in velocity. Near Earth's distance from the Sun, orbital motion is fast. Turning a solar orbit by a full right angle at that distance would require a velocity change greater than Earth's orbital speed itself. The spacecraft would need to redirect a motion of nearly 30 kilometers per second into a new orientation. Chemical propulsion cannot provide that kind of change to a useful scientific spacecraft after launch and Earth escape. This is why the phrase straight up can be misleading. A rocket on Earth rises vertically for only part of its ascent. Very soon, it begins turning sideways. To remain in orbit, it must gain horizontal speed. Altitude alone does not create an orbit. Sideways motion is what allows the spacecraft to keep orbing around Earth without reaching the surface. The same principle applies at the larger scale of the Sun. A spacecraft near Earth is already falling around the Sun. To travel straight away from the ecliptic without carrying much of that circulation, it would have to reshape an enormous existing velocity. Escaping outward can be easier because the spacecraft can preserve the direction it already has. Imagine a stone moving around the rim of a wide circular track. To release it outward, you may only need to increase its speed until the curved path opens into an escape trajectory. The stone continues broadly in the direction it was already traveling. Now imagine asking the same stone to leave the track by moving directly above it. The motion along the rim does not vanish. It must be redirected. The challenge is not the empty region overhead. The challenge is the momentum carried around the circle. This difference lies at the center of interplanetary mission design. Propellant must accelerate not only the spacecraft, but also the remaining propellant that will be used later. Adding more fuel increases mass. The heavier vehicle then requires still more fuel to achieve the same change in velocity. This compounding relationship is described by the rocket equation. It places a severe limit on what chemical rockets can do. A mission cannot simply add fuel without consequence. Tanks become larger, structures become heavier, engines and launch vehicles must grow. Much of the added propellant is spent carrying other propellant before it can be used. For modest maneuvers, this system works extremely well. For a very large heliocentric plane change, it quickly becomes impractical. The problem can be reduced by changing the maneuver's location. A spacecraft in an elongated orbit moves fastest near the Sun and slowest when it is far away. Since plane changes are cheaper when orbital speed is lower, mission planners prefer to alter inclination at the distant part of an orbit whenever possible. This is one reason the outer solar system become useful. Far from the Sun, a spacecraft travels more slowly along its path. A turn made there requires less change in velocity than the same turn attempted near Earth's orbit. If a massive planet is also available, its gravity can bend the path without requiring the spacecraft to supply the entire change through its own engines. The planets are therefore more than destinations. They are moving gravitational landscapes. A carefully timed encounter can alter speed, direction, or both. The spacecraft enters the planet's region of influence on one path and leaves on another, while the total exchange of energy and momentum remains governed by conservation laws. From the planet's point of view, the spacecraft falls inward and then climbs away. From the Sun's point of view, the planet itself is moving throughout the encounter. That motion allows the spacecraft's solar trajectory to change. A minute amount of momentum passes between the two bodies, immeasurably small for the planet, but transformative for the spacecraft. Most gravity assists keep missions near the planetary plane. That is where the planets are found, and it is where their motion is most useful for sending spacecraft inward or outward. But a gravity assist can also bend a path above or below the ecliptic when the encounter geometry is chosen for that purpose. Without such assistance, a spacecraft must rely on propulsion alone. Electric engines offer another possibility. They produce far less thrust than chemical rockets, but they can operate for long periods. Instead of making one powerful turn, an electrically propelled spacecraft can accumulate a large change gradually. The acceleration may be too small to feel. Over months and years, however, the effect grows. The orbit changes a little during each hour of thrust. Speed, distance, and inclination can be adjusted with much greater propellant efficiency than a chemical engine could provide. Yet patience does not remove every difficulty. Electric propulsion requires energy, long operating times, durable components, and careful navigation. A spacecraft far from the Sun receives less sunlight for its power systems. Nuclear sources may help, but they introduce other engineering limits. The mission must survive long enough for its many small changes to add together. Every method involves a trade. Chemical engines provide strong thrust, but consume propellant rapidly. Electric engines conserve propellant, but require time. Gravity assists can produce large changes, but only when a suitable planet and alignment are available. No option simply opens a direct road above the solar system. The plane itself exerts no force. It does not pull spacecraft back toward it like the surface of a stretched sheet. The difficulty comes from initial conditions. Earth, the spacecraft, and nearly every useful planetary encounter already move along the inherited disk. Once a spacecraft has been placed on a steeply inclined solar orbit, it can continue along that orbit without constantly burning fuel. The expense lies mainly in creating the new trajectory. That distinction matters. Space does not resist upward travel. Momentum resists sudden change. The same physical memory that kept the planets circling within a shared plane now accompanies every machine launched from their surfaces. A spacecraft may be newly built, but the motion it carries is older than Earth. To rise far above the ecliptic, it must find a way to turn that inheritance. Humanity has done this most dramatically only once, with a small spacecraft sent first toward the largest planet in the solar system. Its destination was the Sun's unexplored poles. Its ladder was Jupiter. Jupiter was not the destination Ulysses had been built to study. The spacecraft carried no camera, designed to map the giant planet's clouds. No lander for one of its moons, and no plan to remain in the Jovian system. Jupiter was part of the route because its gravity could perform a turn that no practical launch vehicle could provide. Ulysses left Earth aboard the Space Shuttle Discovery on October 6, 1990. After reaching orbit, powerful upper stages sent the spacecraft away from Earth at unusually high speed. Its first long path followed the familiar arrangement of interplanetary travel outward through the planetary plane. For 16 months, it moved toward Jupiter. This outward journey served two purposes. It brought Ulysses to the one planet massive enough to redirect it sharply, and it carried the spacecraft into a region where its orbital speed around the Sun was lower than it had been near Earth. A plane change becomes less expensive when it's performed at lower speed. Near Earth, a spacecraft must travel quickly to remain in solar orbit. Farther from the Sun, the required orbital speed declined. By the time Ulysses reached Jupiter's distance, the motion that needed to be redirected was already smaller. Then Jupiter supplied the rest. On February 8, 1992, Ulysses passed near the planet. Jupiter's gravity drew the spacecraft inward, accelerated it, and curved its path. As Ulysses moved away again, it did not return to the plane from which it had arrived. The encounter bent its trajectory steeply southward. From that moment, Ulysses occupied a solar orbit unlike that of any previous spacecraft. It would travel beneath the planetary plane, pass through high southern solar latitudes, cross the equatorial region, and continue toward the north. The maneuver did not place Ulysses in a tight orbit around the Sun's poles. Its path was broad and elongated. At its farthest point, the spacecraft returned to approximately Jupiter's distance. At its closest, it remained farther from the Sun than Earth. One circuit took a little more than 6 years. Yet, the orbit reached solar latitudes above 80 degrees. From there, Ulysses entered regions of the heliosphere that had never been sampled directly. Nearly every earlier spacecraft had observed the Sun from close to its equator, because nearly every spacecraft remained near the ecliptic. Ulysses could finally measure how the solar environment changed far above and below that narrow observational band. The Sun has no solid surfaces, but it fills the solar system with matter. Its hot outer atmosphere expands continuously into space, producing a stream of charged particles known as the solar wind. This flow carries electrons, protons, magnetic fields, and traces of heavier atomic nuclei outward through the planetary system. Earth is immersed in it. The solar wind presses against our planet's magnetic field, shaping a protective region called the magnetosphere. Changes in the flow can disturb that region, contribute to auroras, and affect satellites, radio signals, and electrical systems. Before Ulysses, measurements of this wind had been made mainly from low solar latitudes. Scientists understood that activity near the Sun's equator was complex. Dense streams and faster streams could overtake one another. Magnetic structures rotated with the Sun. Coronal mass ejections sometimes carried large clouds of plasma outward. What remained uncertain was how the wind behaved near the poles. During its first southern passage in 1994, Ulysses entered a broad flow of fast solar wind. Near solar minimum, large coronal holes extended over the Sun's polar regions. Magnetic field lines there opened into interplanetary space, allowing plasma to escape at speeds near 750 kilometers per second. The flow was rapid, but comparatively uniform. Closer to the solar equator, the wind often alternated between faster and slower streams. At high latitude, Ulysses found a more persistent outflow. The Sun appeared divided into different wind regimes with slower, less orderly conditions near the equatorial activity belt and fast streams emerging from the polar regions. Months later, Ulysses passed over the northern solar latitudes. the pattern appeared there as well. For the first time, scientists could begin assembling a three-dimensional view of the heliosphere from direct measurement rather than inference. The solar wind was not leaving the sun in the same way at every latitude. Its speed and structure depended on the changing arrangement of magnetic fields across the solar surface. Ulysses also measured the magnetic field carried through interplanetary space. The sun's rotation winds this field into a broad spiral as the solar wind moves outward. Near the planetary plane, this spiral had been studied for decades. Ulysses revealed that the field's strength did not decline toward the poles. In the simple way some models had expected, the heliosphere was more interconnected than a flat view had suggested. Particles and fields could move across latitudes. Solar activity could affect regions far from the place where it began, structures created nearer. The equator did not always remain confined there. The spacecraft returned to the polar regions when the sun was more active. Solar activity rises and falls through an approximately 11-year cycle. During minimum, the magnetic arrangement is comparatively ordered, with large polar coronal holes and activity concentrated nearer the equator. As maximum approaches, the field becomes more complicated. Sunspots appear at wider latitudes, eruptions become more frequent, and the magnetic poles prepare to reverse. Ulysses survived long enough to observe both conditions. During its later high-latitude passages, the clear division between fast polar wind and slower equatorial wind became less distinct. The turbulent activity associated with solar maximum reached across a wider range of latitudes. The polar environment was no longer a stable region isolated from the changing sun below. This was one of the mission's deepest contributions. A single pass might have shown how the sun behaved at one stage of its cycle. Repeated passages revealed that the heliosphere changes as a whole. Its large-scale structure breathes with solar activity, becoming more ordered, and then less ordered over spans longer than most spacecraft missions are designed to survive. Ulysses completed 3 broad surveys of the sun's high latitudes. Each occurred under different solar conditions. Together, they allowed researchers to compare the heliosphere across nearly 2 full activity cycles. The spacecraft was also listening to environments far beyond the sun itself. Its instruments detected particles arriving from interstellar space, material moving through the solar system from the galaxy around it. It measured cosmic rays entering the heliosphere and how the solar magnetic field altered their paths. These high-energy particles arrive from outside the solar system. Their numbers near Earth are influenced by solar activity. When the sun is active, its extended magnetic environment deflects more of them. During quieter periods, more can penetrate inward by traveling far from the ecliptic and across a range of solar latitudes. Ulysses helped reveal how this shielding varies through space and time. It also detected small grains of interstellar dust. The solar system moves through a thin cloud of material in the local galactic environment. Some dust grains from that cloud pass through the heliosphere. Ulysses measured their direction and behavior, distinguishing them from particles produced within the solar system. Even Jupiter continued to appear in the mission's data long after the flyby. Ulysses detected streams of extremely small dust particles escaping from the Jovian system. Electromagnetic forces associated with Jupiter accelerated these grains and sent them outward. Their arrival at the spacecraft created a moving connection between the giant planet and regions far beyond it. A mission built to study the sun had become a survey of many things crossing the heliosphere. Solar wind moved outward, cosmic rays moved inward, interstellar dust passed through, charged grains escaped from Jupiter, magnetic fields connected distant regions, carrying evidence of events that had happened elsewhere. Space above the planetary plane was not empty in the scientific sense. It contained fewer worlds and fewer for familiar destinations, but it was crossed by fields, particles, and streams that could be studied more clearly away from the crowded geometry of the ecliptic. Ulysses itself was a modest machine. Its main body was only a few meters across, surrounded by booms and antennas. Because it traveled as far as Jupiter's orbit, solar panels would not have provided dependable power throughout the mission. It relied instead on a radioisotope generator, converting heat from radioactive decay into electricity. The available power gradually declined. The spacecraft also had to keep fuel from freezing in its small attitude control system. As electrical output fell, engineers carefully managed heaters, instruments, and communications. They found new operating methods and extended a mission originally planned for 5 years into one lasting almost 19. By its final years, maintaining the spacecraft had become increasingly difficult. Commands still crossed the distance from Earth. Data still returned through the deep space network, but the slow decline of onboard power could not be reversed. On June 30th, 2009, the mission ended. Ulysses remained in its long solar orbit, still climbing and descending through latitudes that no operating spacecraft occupied. Its instruments were silent, but the path Jupiter had given it continued. The mission had demonstrated more than a method of reaching the sun's poles. It showed why such a journey demanded a different kind of planning. Ulysses did not overcome the cost of leaving the ecliptic with a larger fuel tank. It changed the place where the turn occurred, reduced the speed at which the turn had to be made, and allowed a planet to provide the force. The solution was written into the architecture of the solar system itself. A spacecraft born within the planetary plane traveled outward to the largest world in that plane. Jupiter then lifted it away, converting an ordinary interplanetary path into a high-latitude orbit around the Sun. For nearly 19 years, Ulysses followed that borrowed curve, and above the planetary paths, it found the solar wind moving through a wider sky. The path away from the planetary plane does not always require one dramatic turn. It can be built gradually, encounter by encounter, with each passage changing the orbit by only a few degrees. The result may look modest when compared with the steep path of Ulysses, but the method reveals another way. Spacecraft move through the solar system. Solar Orbiter began that patient climb in February of 2020. The mission, led by the European Space Agency with participation from NASA, was designed to study the Sun from nearby space. It carries instruments that sample particles and magnetic fields around the spacecraft, along with telescopes that observe the solar surface and atmosphere from a distance. Its goals require both closeness and perspective. From Earth, the Sun is seen near its equatorial region. The planet's orbit remains close to the solar equator, as do the paths of most observatories. The poles rotate into view only at a shallow angle, leaving their magnetic structure difficult to study. Solar Orbiter could not simply turn toward them after launch. Like every spacecraft leaving Earth, it inherited a solar orbit moving near the ecliptic. Its launch vehicle placed it on a path toward the inner solar system, but most of the orbital direction remained similar to that of the planet from which it came. The spacecraft would need help from Venus. Venus travels closer to the Sun than Earth and completes an orbit in less time. By arranging repeated encounters with the planet, mission designers created a sequence in which Solar Orbiter could return again and again, each time approaching from a slightly different direction. The flybys do not lift the spacecraft all at once. Each one bends the orbit by a limited amount. The first encounters helped adjust its distance from the Sun and align later passages. Then, in February of 2025, a close approach to Venus raised the spacecraft's orbital inclination to about 17 degrees relative to the Sun's equator. That angle is far smaller than the inclination reached by Ulysses. Yet, it was enough to change what the cameras could see. Solar Orbiter began obtaining direct views of the solar polar regions from outside the narrow band, occupied by Earth and most other spacecraft. Surface features previously compressed near the edge of the visible disk could be observed from a higher latitude. The view was not from directly overhead. It was more like standing on a low hillside after spending a lifetime at ground level. The summit remains distant, but its shape becomes clearer because the line of sight is no longer pressed against the horizon. Further Venus encounters can continue the climb. A planned flyby in December of 2026 is intended to raise the inclination to roughly 24 degrees. Later mission phases may carry Solar Orbiter higher still, allowing the polar landscape to be examined from progressively better angles. Every increase is purchased with time and geometry, rather than a large engine burn. The spacecraft must meet Venus at a precise location. Venus must be moving in the correct part of its orbit. The arrival direction must be chosen, so the planet's gravity turns the path toward a greater inclination without sending the spacecraft too close to the surface or placing it on an unusable solar orbit. A gravity assist is sometimes described as a slingshot. That image is helpful, but it can also make the event seem sudden and simple. In practice, the maneuver begins long before the spacecraft reaches the planet. It begins with the launch date, the shape of the transfer orbit, and small corrections made across millions of kilometers. By the time the encounter occurs, much of the outcome has already been decided. The spacecraft falls into the planet's gravitational field. Its speed relative to the planet rises as the distance decreases. The path curves. After passing the closest point, the spacecraft climbs away again and loses the speed it gained during the approach. Relative to Venus, it departs with nearly the same speed it had before the encounter. Relative to the Sun, however, the direction has changed. Venus itself is moving around the Sun. The spacecraft has interacted not with a stationary world, but with a planet carrying its own orbital momentum. The tiny exchange between them reshapes the spacecraft's heliocentric path. The effect on Venus is real, but far too small to measure. The planet is immensely more massive than the spacecraft. Any change in its orbit is lost within a scale so small that it has no practical consequence. For Solar Orbiter, the same exchange determines years of future travel. This is orbital engineering at its most restrained. No engine needs to fire through the entire turn. No enormous reserve of propellant must be carried from Earth. The planet provides the curvature, while spacecraft arrives at the correct place and allows gravity to work. Solar Orbiter's repeated flybys also show why mission time can serve as a kind of resource. A more powerful propulsion system might achieve some changes sooner. A patient trajectory can replace part of that power with years. The spacecraft completes orbits, waits for Venus to return, and meets the planet again when the geometry becomes useful. The climb emerges from repetition. One passage changes the orbit. The new orbit creates the next encounter. The next encounter makes another change possible. A mission can gradually leave the plane without ever performing a single overwhelming maneuver. There is a mirror image of this problem closer to the Sun. Parker's solar probe was not designed to rise toward the solar poles. Its task was to descend deeper into the Sun's gravitational environment than any previous spacecraft, eventually passing through the outer solar atmosphere. Falling toward the Sun might sound easy. Gravity is pulling inward, and the Sun is the most massive object in the solar system. A spacecraft released near Earth might seem as though it should simply drop toward the center. But Earth is moving sideways. A spacecraft leaving Earth carries that same motion, nearly 30 kilometers per second around the Sun. Without removing much of it, the spacecraft continues to orbit instead of falling directly inward. The inherited velocity that makes climbing out of the ecliptic expensive also makes reaching the Sun expensive. In one case, the spacecraft must redirect the motion. In the other, it must reduce it. Parker Solar Probe used Venus 7 times. Each encounter removed part of the spacecraft's orbital momentum relative to the Sun. The resulting orbit became narrower and more elongated. Its closest point moved inward while the probe accelerated to immense speed each time it approached the Sun. The final planned Venus encounter occurred in November of 2024. That passage placed Parker on the orbit used for its closest solar approaches, bringing it to within several million miles of the visible surface. There, protected by a heat shield, the spacecraft entered a region where solar material had begun escaping into space. Solar Orbiter and Parker travel for different reasons. One gradually changes viewing latitude. The other gradually reduces its closest distance to the Sun. Yet their paths are shaped by the same underlying limit. A spacecraft cannot ignore the motion it inherited from Earth. Parker could not simply point toward the Sun. Solar Orbiter could not simply point toward the poles. Both needed Venus to adjust a path that onboard propulsion could not efficiently reshape by itself. The planet became a tool shared across 2 missions. For Parker, Venus removed solar orbital energy. For Solar Orbiter, Venus changed inclination. The difference came from the angle of approach and the direction in which each spacecraft passed the moving planet. A single world can therefore perform several kinds of work. It can accelerate a spacecraft outward, slow one moving inward, or bend an orbit away from its original plane. Gravity itself does not choose the result, the geometry does. This principle has guided spacecraft since the early years of planetary exploration. Mission designers draw possible paths through a moving solar system, searching for encounters that convert one orbit into another. The calculations must account for planetary positions years ahead, the mass of each world, the speed of the spacecraft, and the limits of instruments and communication systems. A useful route may open only during a narrow launch period. Miss that period, and the planetary arrangement may take months, years, or decades to return. Some paths depend on combinations that occur rarely enough to shape an entire generation of missions. Behind every gravity assist is a long chain of human attention. Engineers compare trajectories. Scientists decide what observations must be protected. Navigation teams refine the approach. Deep space antennas measure the spacecraft's position from signals that may have traveled for many minutes before reaching Earth. The final correction can be small. A brief engine firing far from the planet may shift the future flyby by hundreds of kilometers. The adjustment seems slight when it occurs, yet it changes where the spacecraft will be years later. This is one of the quieter truths of spaceflight. Large journeys are often controlled through small changes made early. An orbit is allowed to unfold. Gravity carries the spacecraft most of the way. Engineers do not hold the vehicle on a rigid line through space. They shape its fall and then watch as that shape develops around the Sun. The resulting path can resemble a conversation between many moving bodies. Earth provides the starting motion. A launch vehicle adds a measured change. Venus bends the orbit. The Sun accelerates and slows the spacecraft according to its distance. Each influence becomes part of the route. Solar Orbiter continues around the Sun on such a path. With each rise above the familiar viewing plane, the polar regions become less hidden. The magnetic fields emerging there can be traced more clearly. The movement of plasma across the solar surface can be compared with conditions measured around the spacecraft. The poles matter because the Sun's magnetic field is not permanent in one orientation. During each activity cycle, the global field reorganizes and reverses. The polar regions are central to that change, but they have long been among the least directly observed parts of the star. A higher viewpoint may help connect what happens near the surface with the solar wind moving through the heliosphere. It may also reveal how magnetic patterns are carried from lower latitudes toward the poles, stored there, and later drawn into the next cycle of activity. The spacecraft does not need to reach 90 degrees to make these observations valuable. A partial climb changes the geometry enough to uncover features that remain difficult from Earth. The mission gains knowledge not by standing directly over the pole, but by moving far enough away from the old line of sight. There may be no universal up in space, yet a few degrees of newly earned altitude can still transform what a star allows us to see. For a spacecraft, direction can be calculated from stars, gyroscopes, and radio signals. For a human body, the question is more intimate. You do not experience up as a diagram. You feel it through several systems working together. The inner ear senses acceleration and the orientation of the head. The eyes read walls, horizons, and familiar shapes. Muscles and joints report pressure, balance, and the distribution of weight. On Earth, these signals usually agree. Your feet press against the floor. The fluid-filled structures of the inner ear respond to gravity. Your eyes see a room arranged around the same downward direction. The brain combines these messages so completely that the result does not feel like an interpretation. It feels like reality. In orbit, that agreement begins to break apart. The organs of balance inside the inner ear evolved in an environment where gravity was always present. Small structures, called otolith organs, contain tiny mineral particles resting on sensitive cells. On Earth, their weight helps the brain recognize tilt and linear acceleration. During free fall, those particles no longer settle in the familiar way. The eyes may still see what appears to be a floor. Handrails, lights, storage panels, and labels provide a visual orientation, but the inner ear does not confirm it, and the body does not feel a steady pressure beneath the feet. The result can be confusion. Many astronauts experience space motion sickness during their first days in orbit. The symptoms vary. Some feel nausea. Others report headaches, fatigue, loss of appetite, or an uneasy sensation that the room has turned around them. The movement itself is not always the main cause. The deeper problem is disagreement between senses that have spent an entire lifetime delivering one shared answer. The brain expects gravity, but the expected signal is absent. Vision may suggest one direction, while the vestibular system reports something less certain. Over time, adaptation begins. The brain learns to rely more heavily on visual cues, a surface marked as the deck becomes down because the crew treats it that way. Equipment is placed in consistent orientations. Labels face a common direction. Work areas are arranged to help the mind preserve a useful frame of reference. This chosen down is practical, but not physical. An astronaut can rotate slowly and watch the room appear to turn. A colleague, working on what seems to be the ceiling, may feel upright from their own point of view. Passing through a hatch into a differently arranged module can cause the entire visual world to flip. Nothing has changed in the gravitational environment, only the interpretation has changed. This flexibility becomes normal for experienced crews. Objects can be stored on every surface. A computer mounted overhead is no less accessible than one placed beside the feet. A person can sleep attached to a wall, secured only to prevent drifting through the cabin. Yet, the body is doing more than learning a new visual language. Without weight, muscles no longer work against gravity in the usual way. Bones receive less mechanical loading. Fluids that normally collect somewhat lower in the body shift toward the chest and head. The face can appear fuller, while the legs become thinner. Over longer missions, these changes matter. Muscles weaken when they are not regularly challenged. Bones lose mineral density. The cardiovascular system adapts to moving blood without the constant pressure difference between the head and feet found on Earth. Astronauts exercise for hours each day to reduce these effects. Resistance machines imitate some of the work gravity once supplied. Treadmills hold the body against a moving surface with straps. Stationary bicycles maintain endurance without requiring the rider to remain on a seat through weight alone. Exercise helps, but it does not recreate the complete environment of a planet for journeys lasting many months, or settlements intended to remain in space for years. Another solution has often been proposed: rotation. Imagine a large spacecraft shaped partly like a wheel. As the structure turns, people inside move in circles. Their bodies naturally tend to continue along straight paths, but the outer wall keeps redirecting them toward the center. The wall presses against their feet, producing the sensation of weight. In the rotating frame, the experience would feel like a force pulling outward. Down would point toward the rim, up would point toward the central axis. No planet would be required. The habitat would manufacture a local, vertical direction from motion. This is often called artificial gravity, although no new gravitational field has been created. The sensation comes from continuous acceleration as the rotating structure bends each person's path into a circle. The result could still feel convincing. A person standing on the inner surface of a large rotating ring might walk, sleep, pour water, and place objects on tables much as they would on Earth. Their feet would press against the floor. Their muscles would carry weight. The inner ear would once again receive a consistent directional signal. The body does not need to know whether the pressure comes from a planet or a rotating wall. It only needs the signals to agree. Designing such a habitat is not simple. If the structure rotates too quickly, moving the head can create uncomfortable sensations. The inner ear detects the combined effects of rotation and motion within the habitat. A person turning or bending may briefly feel as though the room is moving in an unexpected direction. This is related to the Coriolis effect. In a small, rapidly rotating station, walking toward the center or away from it would change a person's speed relative to the rotation. The body could feel pulled sideways. Objects dropped from the hand might follow curved paths rather than falling in a straight line toward the floor. A larger habitat could rotate more slowly while producing the same apparent weight at its rim. This would reduce some of the disorientation. Size becomes part of comfort. The structure must also be strong enough to withstand the forces produced by rotation. Every section of the ring pulls on the sections beside it. The faster the habitat spins and the greater its radius, the more carefully its materials and joints must be designed. The system must remain balanced. Water, cargo, equipment and people move through the structure. If too much mass gathers on one side, the rotation may become uneven. Pumps, bearings, docking systems, and attitude control equipment would all need to operate while part of the spacecraft is turning. A rotating habitat would therefore create down only through continuous engineering. Its vertical direction would be local, deliberate, and maintained. Near the axis, the sensation of weight would become weaker. A person climbing inward from the rim would gradually feel lighter. At the center, where the circular speed is lowest, they could float again. One structure could contain both a floor-bound environment and a region of near weightlessness, separated only by distance from the axis. Up would become a place you could travel toward. A ladder extending inward would lead from apparent gravity into free fall. The journey might take only a few minutes. The direction would not be defined by a planet below, but by the geometry of the rotating home itself. This kind of environment would change ordinary architecture. Floors would curve around the ring. Ceilings would face the axis. Buildings or rooms could continue along the inner circumference. until they return to their starting point. Two people standing far apart on the ring would each call a different direction down. Their feet would point away from the common center, but not parallel to one another. Each local vertical would follow its own radius through the habitat. This resembles life on Earth more closely than it first appears. People standing in North America and people standing in Australia do not share the same geometric down. Their feet point toward Earth's center from different sides of the planet. They feel upright because each person experiences gravity locally. A rotating habitat would follow the same pattern with a different cause. Across generations, a community born inside such a structure might accept its orientation without question. Children could learn that falling means moving toward the outer hull. The central axis might seem naturally overhead, even though someone outside the habitat would see no universal reason to describe it that way. Their language would grow around their environment, so would their instincts. Returning to a non-rotating spacecraft might feel as disorienting to them as orbital flight feels to someone raised on Earth. Arriving on a planet could bring another adjustment, with gravity pointing toward a center outside the architecture, rather than away from an axis within it. Up and down would remain bodily truths. They would simply change from place to place. For now, astronauts live between these ideas. They leave a world where down is provided by Earth. They enter vehicles where orientation is chosen visually. They may one day travel in habitats where rotation restores weight through a carefully designed curve. The direction does not disappear. It is reassigned, and wherever the body finds a steady pressure, a stable view, and a consistent acceleration, it begins to build a new world around the answer. The solar system's plane is not aligned with the larger structure that contains it. The Milky Way is also flattened, but its disk lies at a different angle. The ecliptic cuts across the galactic plane rather than resting inside it. The two systems formed from different clouds at different times under different conditions, and they kept different rotational memories. This means that solar up is not galactic up. A spacecraft traveling toward the north ecliptic pole would be leaving the planetary plane, but it would not be moving directly above the Milky Way's disk. The galaxy would remain tilted across its path. The difference is large. The ecliptic is inclined by roughly 60 degrees to the galactic plane. From Earth, this layered geometry appears in the sky as two separate bands. The zodiac traces the neighborhood of the ecliptic, while the luminous path of the Milky Way follows the galaxy's disk. They cross. To an observer under a dark sky, the intersection is not marked by a line or boundary. It appears only through the movement of the sun, moon, and planets against a denser background of distant stars. For early sky watchers, these patterns offered two different kinds of order. The wandering planets remained close to one narrow path. The Milky Way formed a broader river of light with a completely different orientation. Long before the physical structure of either system was understood, people were already seeing one disk from inside another. The galaxy's disk is vastly larger than the planetary system. The Sun lies about 26,000 light-years from the Milky Way's center, within a smaller structure often called the local arm or Orion spur. It moves around the galactic center, along with nearby stars, gas clouds, and the invisible mass that contributes to the galaxy's gravitational field. One full circuit takes roughly a few 100 million years. Human history occupies almost none of that orbit. Recorded civilization represents only a tiny arc. Even the entire existence of our species covers a small fraction of one galactic year. Yet the motion is continuous. The night sky appears stable because the distances are so large. Constellations shift gradually, not because the stars are fixed, but because their movement becomes visible only across long spans of time. The Sun is also moving vertically through the galaxy's disk. It does not remain at one exact height above the galactic midplane. The gravity of stars, gas, dust, and dark matter draws it toward the denser central region of the disk. As the Sun passes through, its motion carries it beyond the middle before gravity slows the rise and draws it back again. The solar system follows. Earth, the Moon, the planets, and every spacecraft remain bound to the Sun, while the entire system moves above and below the galaxy's central plane. This vertical motion unfolds across tens of millions of years. From within the solar system, nothing feels different. The planets continue their familiar orbits. The Sun appears in Earth's sky. Seasons pass. No local instrument senses a galactic flaw rising and falling beneath the planets. The motion becomes meaningful only when measured against distant stars and models of the galaxy's mass. This is another example of orientation depending on scale. For someone standing on Earth, down points toward the planet's center. For a spacecraft navigator, solar coordinates may define inclination above or below the ecliptic. For a galactic astronomer, the important reference may be distance from the Milky Way's midplane. Each system is valid within its own purpose. None is universal. The galaxy's shape also comes from rotation, but it did not form exactly as the solar system did. The young Milky Way grew through the collapse of matter, the merging of smaller systems, the cooling of gas, and the formation of generations of stars. Gas could collide, lose energy, and settle into a rotating disk. Stars already formed could retain thicker and more varied orbits. The galaxy therefore contains several overlapping structures. There is a thin disk where much of the gas, dust, and younger stellar population is concentrated. There is a thicker disk containing older stars, with a wider range of motions above and below the midplane. There is a central bulge, a bar, spiral structure, and an extended halo containing old stars, globular clusters, and dark matter. The Milky Way is flattened, but not thin in the way an illustration might suggest. Its visible disk has depth. Stars move on orbits that carry them through different heights. Gas clouds rise and settle. Supernovae and stellar winds push material away from crowded regions, while gravity draws much of it back. Even within the galaxy, the plane is not an unbreakable surface. It is an average, a statistical shape created by billions of objects moving under a shared gravitational field. The solar system is one small traveler within that distribution. Its ecliptic orientation does not align with the galaxy because the cloud that formed the Sun carried its own local angular momentum. A molecular cloud inside the Milky Way can rotate in a direction unrelated to the larger galactic disk. When part of that cloud collapses, the resulting star system preserves the local spin rather than copying the orientation of the galaxy around it. Other planetary systems follow their own planes. Some appear neatly aligned with the equators of their stars. Others are tilted. A few planets orbit in steeply inclined or even polar paths relative to the rotation of their host stars or the orbits of companion stars. The universe permits many arrangements. What is expensive for a spacecraft to achieve after formation may be natural for a system born with a different orientation. A planet does not need to spend fuel to occupy a polar orbit if gravitational interactions placed it there. Long ago, a stellar companion can reshape a planetary system over millions of years. Encounters during formation can tilt disks, scatter worlds, or leave orbits that seem unusual only when compared with our own. This distinction matters. The difficulty of reaching a direction does not mean that the direction itself is rare everywhere. Within our solar system, most useful mass remains near the ecliptic. Planets, major moons, and much of the smaller body population stay close to the old disk. The available gravity assists are found there. The launch point is found there. The inherited velocity lies there. Elsewhere, another system may begin from a different geometry, a planet, might travel along a path that repeatedly carries it above and below the orbit of two stars. To observers within that system, the unusual orbit would not feel like a spacecraft climbing against momentum. It would simply be the planet's ordinary motion. Formation sets the starting conditions. Navigation must work with what formation has already given. The same principle extends beyond individual stars. Galaxies in a group are not all oriented the same way. Their disks point in different directions. Some are seen face-on from Earth, showing spiral structure. Others are seen edge-on, appearing as thin bands divided by lanes of dust. No common-up organizes the group. The Milky Way and the Andromeda Galaxy approach each other within the local group, but their disks are tilted relative to one another. Smaller galaxies move around them on additional planes, often shaped by complex histories of capture and interaction. Farther out, galaxy groups gather into clusters. Clusters do not usually resemble one flat rotating disk. They are three-dimensional collections of galaxies, gas, and dark matter. Their members follow varied paths through a shared gravitational well. At larger scales still, clusters and galaxies trace filaments. These structures form the cosmic web, a network of dense nodes, long strands, sheets, and broad voids. Gravity has drawn matter into this pattern over billions of years, beginning with small variations in the early universe. The web has direction locally. A galaxy may move along a filament. Matter may fall toward a cluster. A sheet may define a temporary geometric plane across millions of light years, but no single orientation extends through all of it. The largest observable patterns do not point toward one cosmic ceiling. Modern cosmology describes the universe on sufficiently large scales as approximately uniform in every direction. Local regions contain structure, but when averaged across immense distances, no preferred global direction has been established. There is no known top of the universe, no lower side, no external vantage point from which the cosmos can be seen resting in a larger room. The words above and below remain useful only when attached to something nearby. Above Earth, below the ecliptic, north of the galactic plane, toward one side of a filament. Each phrase requires a reference. Remove the reference, and the direction becomes incomplete. This may seem abstract, but your body performs the same act every moment. It chooses Earth as the reference without asking. The planet is close, massive, and steady enough to define the answer. Gravity provides the pull. Architecture reinforces it. Memory makes it familiar. The certainty comes not from the universe as a whole, but from the strength of one local relationship. Beyond Earth, the relationships change. A spacecraft can carry coordinate systems, star trackers, and maps from one region to another. It can preserve a chosen orientation through software and spinning wheels, but the deeper physical meaning of up will continue to shift with every new scale. The solar system turns within the galaxy. The galaxy moves within a group. The group lies within a larger web, and none of those structures agrees on which way the sky should face. A reference plane can be invisible and still shape what you see. Earth's orbit around the Sun provides one of astronomy's most useful examples. The path defines the ecliptic, a geometric plane passing through the center of the Sun and extending outward in every direction from Earth. That plane appears projected across the sky. The Sun seems to follow it through the year. The planets remain close to it. The Moon wanders above and below, but not by very much. The familiar constellations of the zodiac lie along this same broad band because they form the background through which the nearby members of the solar system appear to move. For early observers, this narrow path was evident before it was explanation. They could watch Mars move against the stars. They could follow Venus near sunrise or sunset. They could record where the Moon crossed the sky and notice that these wandering lights did not appear anywhere at random. They stayed within a shared region. The people making those observations were standing inside the planetary system's old disk, looking outward along it. They could see the pattern without yet knowing that the pattern came from a flattened cloud that had existed before Earth. Even now, the ecliptic is easier to recognize through motion than through sight. There is no glowing line across the sky. The plane becomes visible only because the sun, moon, and planets keep returning to it. The moon provides a delicate variation. Its orbit around Earth is tilted by a little more than 5 degrees relative to the ecliptic. That angle seems small, but it determines when eclipses can happen. If the moon orbited in exactly the same plane as Earth's path around the sun, a solar eclipse would occur at every new moon. A lunar eclipse would follow at every full moon. The three bodies would align twice during each lunar cycle. Instead, the moon usually passes above or below the necessary line. Its orbit crosses the ecliptic at 2 points called nodes. An eclipse can occur only when the sun is also near one of those crossing points, as the moon becomes new or full. This creates eclipse seasons. The events are not rare because the moon travels far from the ecliptic. They are limited because even a small difference between two planes is enough to break the alignment most of the time. A few degrees can separate darkness from daylight. The same geometry appears around Saturn. The planet's rings occupy the plane of Saturn's equator, which is tilted relative to its path around the sun. As Saturn completes its long orbit, our viewing angle changes. For years, the rings appear broadly open. Then the angle narrows until the ring system turns almost edge-on from Earth. At that moment, the enormous structure can seem to fade. The rings extend across hundreds of thousands of kilometers, yet their vertical thickness is extremely small compared with their width. When seen from the side, the broad reflective surface is reduced to a narrow line. Nothing has happened to the rings themselves. Only the viewpoint has changed. This is one reason direction matters so deeply in astronomy. Objects are not understood by position alone. The angle from which they are seen can hide a structure, reveal it, or make it appear completely different. A spiral galaxy viewed face-on displays its arms. The same kind of galaxy viewed edge-on becomes a thin luminous band, often divided by dust. A planetary disk surrounding a young star may show rings and gaps from above, while the same disk seen from the side becomes a narrow lane blocking the star's light. Perspective is not an inconvenience added to observation. It is part of the evidence. Spacecraft are often sent into unusual orbits because a new angle reveals information unavailable from a familiar one. Earth observation satellites provide a nearby example. Many follow nearly polar paths, carrying them over high northern and southern latitudes as the planet rotates beneath. Over time, the spacecraft can observe most of Earth's surface. A satellite remaining above the equatorial region would repeatedly pass over a more limited band. The polar orbit trades one orientation for broader coverage. Changing the plane around Earth is far easier than changing the plane around the sun. The speeds, distances, and gravitational environment are different. Launch sites can also be chosen to help. A rocket sent toward a polar orbit may rise from a coast where its path avoids populated land, and where Earth's rotation does not add unwanted eastward velocity. Even here, close to home, inclination is never a decorative number. It determines what the spacecraft can see, how often it can return, how sunlight reaches its instruments, and which regions remain accessible. The International Space Station follows another carefully chosen angle. Its orbit is inclined enough to pass over a wide range of populated latitudes, while remaining reachable from launch sites used by different participating nations. The path reflects geography, engineering, and cooperation written into one number. Every orbit carries such history. Some were shaped by the rotation of a forming disk, some were altered by collisions, or close encounters. Others were selected in control rooms and launch windows by people balancing fuel, purpose, risk, and time. The result is a collection of planes nested around planets, moons, and stars. Astronomers describe them through coordinate systems. The celestial equator extends Earth's equator into the sky. The ecliptic follows Earth's orbit. Galactic coordinates use the Milky Way's disk. A spacecraft mission may define its own frame around a target body. No system is the final one. Each is a tool chosen for a particular question. This may be the most useful way to think about up beyond Earth, not as a lost direction, but as a direction waiting for a reference. On the surface of a planet, the reference is supplied by gravity. Around a star, it may be supplied by the shared plane of orbiting worlds. Inside a galaxy, it may be supplied by the disk of stars and gas. Change the question and the frame may change with it. A direction that seems vertical in one system can become diagonal in another. A spacecraft climbing above the ecliptic may still be moving through the Milky Way's disk. A person floating inside a station may be upside down relative to Earth, while feeling no inversion at all. There is no error in these different descriptions. They are statements about different relationships. This is also true of the sky above you now. The floor beneath you points toward Earth's center. The roof points away. The planet is turning, so the direction called up changes continuously relative to distant stars as you float and rotate through day and night. You do not feel that change. Gravity remains aligned with the body. The room moves with the ground. Everything nearby preserves the same local agreement. Meanwhile, Earth travels around the Sun. The solar system moves through the galaxy. The galaxy moves among neighboring galaxies. The familiar vertical line passing through the room participates in all of these motions without belonging permanently to any of them. For a few hours, it feels fixed. That is enough for architecture, balance, and sleep. The universe does not need to provide one permanent direction for local certainty to be real. It only needs to provide a relationship steady enough to live within. There is no moment when space announces that you have crossed from down into up. No boundary passes over the spacecraft. No instrument detects a change in the fabric of the universe. The engines may fire, the orbit may tilt, and a familiar plane may begin to fall away behind you. But space itself remains indifferent to the label. The direction exists only because something else gives it meaning. Earth gives it meaning through gravity. The solar system gives it meaning through the shared plane of the planets. The Milky Way gives it meaning through its disk of stars, gas, and dust. Each structure provides a temporary frame, useful within its own scale, and incomplete beyond it. This does not make direction unreal. It makes direction relational. A shoreline has an inland side because the sea lies beside it. A mountain has a summit because lower ground surrounds it. A planet has an outward direction because matter gathers toward its center. Remove the reference and the word remains, but the geometry behind it disappears. Spaceflight makes this visible in a way life on Earth rarely does. A person on the ground can spend an entire lifetime without questioning vertical direction. Gravity answers continuously. The body learns the answer before language begins, and every later experience strengthens it. A spacecraft leaves that certainty behind. At first, Earth still fills the view. The planet is large enough to provide an obvious visual below, even when the crew feels no weight. Then, distance increases. Earth becomes smaller. The surrounding stars no longer arrange themselves around a horizon. Navigation continues, but instinct becomes less useful. The spacecraft may point an antenna toward Earth, an instrument toward the Sun, and a heat shield toward incoming radiation. Each direction is chosen by purpose. None deserves to be called the top. Future travelers may become comfortable with this. They may live inside vehicles that rotate, creating floors along an outer rim. They may move between spinning sections and weightless hubs, passing from one local vertical direction into another during an ordinary day. A child raised there might think of up as the direction toward the center of the habitat. Another child born on Mars would learn a weaker but equally dependable pull toward the Martian ground. Someone living on a small asteroid might secure every step, knowing that a strong jump could carry them far from the surface. Each person would grow around a different agreement with motion. The human body would still seek pressure, balance, and orientation. Architecture would still organize rooms around those needs. Language would still divide nearby space into above and below. But no single version would follow humanity everywhere. This may become one of the more subtle lessons of becoming a spacefaring species. Travel between worlds will not only change distances, calendars, and horizons. It will change the bodily meaning of direction. People may carry several versions of upright within memory, adapting each time they enter a new gravitational or rotating environment. The solar system itself will remain mostly flat. Planets will continue around the sun, along paths inherited from the disk that formed them. Spacecraft will still find efficient routes near those paths, where destinations and useful gravity assists are concentrated. Missions traveling far above or below the ecliptic will remain unusual because unusual angles must be earned. New propulsion may change how the cost is paid. Electric engines can accumulate velocity over long periods. Solar sails may use pressure from sunlight to reshape an orbit without carrying traditional propellant. More distant concepts may one day provide higher exhaust speeds or sustained thrust across years. These methods could make steep solar inclinations more practical. A future observatory might travel toward the ecliptic pole and look back on the planetary system from a great distance. From that perspective, the orbits would appear arranged around the Sun in a flattened pattern, with the planets tracing paths across a common surface. Earth would be difficult to distinguish. The entire world, with its oceans, cities, weather, and familiar downward pull, would become one moving point among others. The direction called up on its surface would rotate every day and sweep through space without leaving a mark. From far above the plane, the solar system might finally resemble the diagrams used to explain it. Yet, even that view would be temporary. The observing spacecraft would still orbit the Sun. The Milky Way would still cross the background at an angle. The solar system would still move through the galaxy, carrying the observer along with it. There would be no final viewpoint outside all motion, only another position, another frame, another local answer. This is why the absence of universal up does not leave the universe without order. The order is found in relationships. Moons circle planets. Planets circle stars. Stars move through galaxies. Galaxies gather into groups and filaments. Gravity, rotation, and momentum shape each level, without requiring them to share one orientation. The result is not a single cosmic map with a top edge. It is a collection of nested motions, each creating its own geometry. For science, this requires precision. A direction must be named with its reference. North of Earth's equator, above the ecliptic, toward the galactic pole, away from the center of a rotating habitat. For daily life, the reference can remain unspoken. The floor beneath you supplies it. Gravity continues drawing every part of the room toward Earth's center. The planet turns, the stars change position, and the local vertical moves with you. Nothing in the body needs to follow the larger geometry tonight. The certainty is local, but it is enough. Beyond the atmosphere, spacecraft continue falling around planets and the Sun. Some remain close to the old plane. Others climb gradually away from it, using years, engines, and carefully borrowed gravity. None discovers a ceiling. None finds a permanent direction waiting beyond the worlds. They find only motion being transformed into other motion, one path bending into another, under forces that have shaped the solar system since its beginning. The question of up, therefore, ends where it began, not with a direction, but with a relationship. Here, Earth answers for you. Farther away, another structure would provide another answer. And beyond every answer, space remains open in all directions. The orbit keeps turning without a ceiling.